Hi students, this is Mr. Yang. In this lesson, we are going to talk about triangle congruence, a completely new concept. We're going to start with the first two, SSS and SAS. You'll see what they mean when we get to the definitions. But first, prior knowledge. How many degrees are there on the inside of a triangle? Well, the answer is 180 degrees. That's something we have learned before. This is called the triangle sum theorem. The reason it's called sum is because we add up all three angles to get 180 degrees. That's why it's called sum. Next, congruence. We have learned the definition in the last unit. Two items having the same size and shape. We use this equal sign with a little squiggly line on the top symbol to represent. The reason we say two items is because you can have 2 points that are congruent, like two sides that are congruent, two lines and two angles, two shapes, whatever. So that's what we just call, we just say two items. C and D, these are basically the application of A. So find the missing angle. We already given a 40 degree, and this is 90 degree. So the question mark would just be 180 degrees minus the 40 degree, and then minus the 90 degrees. So the question mark would be 50 degrees. Part D, that part is mainly for the notation actually. Inside a triangle, we have angle A, B, and C. You can see angle A, angle B, and is given. You're looking for angle C. And when we want to write angle, this is the notation. It's not a less than sign. Its bottom is actually flat. That is angle A. This little m in the front represents the measurement of angle A. So the measurement of angle A is 15 degrees. The measurement of angle B is 65 degrees. It's asking for the measurement of C. So it is going to be 180 degrees minus 65 degree minus 15 degree. And that's going to give you measurement of angle C as 100 degrees. That's question D. Next, before we move on to triangle congruence, we are going to need to understand how are congruent figures defined. Congruent figures. Congruent polygons have congruent corresponding parts. This word is actually going to be the most important word in this whole unit, corresponding. They're matching size and angles. So now you can see whenever we're trying to define these congruent figures, we are going to need to find the matching size and matching angles. So inside a triangle, it will be 3 sides and 3 angles. When you name congruent polygons, you must list corresponding vertices. Vertice is the plural form of vertex. You need to name the corresponding vertices in the same order. So for example, this graph on the right side. A, start with A, B, C, D. A, B, and then C, D. So it's not just alphabetical order. When they actually name this, it does look like it starts on the top left corner, but as you can see, the right side, the figure on the right is not starting at F. So the corresponding point for A is not F, it is actually E. You can think of it as A is the biggest angle in the whole figure, and E is also the biggest angle. And then A equal to B, E is actually going to F, then G, then H. So when we actually name it, position in the statement is very important. First position, A is with E. The second position, B is with F. The third position, C is with G. And then lastly, the D is with H. So that's how everything is corresponding. We just put them in the same position in the name for both figures. Before we get to the next part, let's define something else. Included. Included, for example, let's have a look at this one, angle A and angle B. My angle A is right here, my angle B is right here. And when we say what side is included with angle A and angle B, you can clearly see the answer is AB right here. So in other words, included actually means in between the given items. So you can see angle A is right here, is this angle B is this angle right here, and the side is between angle A and angle B. It has nothing to do with C. So that's kind of what included means. Next, if we have a look at the other one, what angle is included with CA and BA? Again, the notation, we had talked about this in the last unit. The little bar on the top indicates this is actually a line segment, and we use that symbol to represent a side of any shape. So side CA is right here, side BA is right here. And these two sides, you can see clearly, form this angle. Or in other words, this angle is included by these two sides. So angle A is included with CA and BA. And from the context of these questions, what does the word included mean in geometry figure? It just means in between the given items. Next, some practice on corresponding parts. H, I, J, K, and L, M, N, O. Like I've talked about in the definition part, the position is basically telling us what are corresponding. When we say corresponding parts, this is a four-sided shape. So clearly there will be four sides and four angles that are corresponding. So first, H and L. That's angle H is congruent to angle L. Then we just move on. The second letter is I and M. So they are corresponding. Third one, J and K. Now J and N. And then lastly, K and O. So these are the angles that are corresponding. We can use one letter to just represent the angle because there's only one angle for the point, for H. But that's not the only way to name an angle. We can also talk about the 3-letter convention to actually name angles. So we'll talk about that in an example. Now let's have a look at the side. HI, typically each side is consisting of 2 points. So HI, the first 2 letters, is corresponding with the first 2 letters in the second shape. So HI is congruent with LM. IJ is congruent with MN. And then JK is congruent with NO. Lastly, or you can have a look at the figure, HI, IJ, JK. Lastly, KH, that is corresponding with OL. This is not the only one to write this. So if we want to name the side, we can choose to flip the letters. So this could also be IH, that is congruent to ML. That works as well. You just need to flip the letters on both sides for both figures. So that's corresponding parts. Now it's time to define triangle congruence. First triangle congruence theorem is SSS, which actually represents side, side, side. And theorem typically are things that have been proven by mathematicians that we don't have to prove, we can just use it. Because mathematicians have helped us, so they know this is something that's for sure going to be right, for sure going to be true, so they have already proven it for us. And the definition for, the definition for triangle congruence theorem with SSS, if all 3 sides of one triangle are congruent to 3 sides of another triangle, then the triangles are congruent. You see this 1 bar, same, 2 bar, same, and 3 bar, same. And these, again, are the marks that we draw when we want to indicate the 2 sides in 2 different figures are the same, are congruent. Real-world connection. 2 identical sets of 3 boards each are fastened together. Are these 2 different triangles, or are they just oriented differently? The answer is they are just oriented differently. If they're identical sets of three boards, basically saying these 2 are the same boards, these 2 are the same boards, and these 2 are the same boards, then based on the definition we just talked about, SSS, these 2 triangles are congruent triangles. So that means they are basically the same triangle, just oriented differently. This is what makes triangular shapes so sturdy and why they are used to build things. I'm assuming many of your houses actually have the triangular shape of roof instead of a flat one. And this is the reason. Once the 3 set lengths are set, you can only make 1 triangle. Well, these 2, kind of like we can make 2 triangles, but they're exactly the same triangle. So that's why it's still 1 triangle. The only difference will be how it's oriented and or flipped. Part B, think about how these boards are fastened together. Which shape would be stable and why? Clearly the one on the right is going to be more stable, and the reason is exactly this, what we just defined. Every single triangle is set, you can't move it. For this one, you can basically say like drag these two corners, and you can make like into a straight line. Or if you push these two in, you can make like a straight line this way. You can clearly move that shape. But with the triangle, this is already sturdy. This is set. You can't change anything. But when you put on two more, you also can't change those. And you can even add more. And if you add more to actually form, say, like a hexagon, that's also going to be a very sturdy shape. Now let's move on to the next one. SAS, Triangle Congruence Theorem. That stands for side, angle, side. If two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the two triangles are congruent. I do need to emphasize on included angle for this. This SAS is a very specific order. The angle has to be in between the two sides. So as you can see, one bar here, two bar here. It didn't just pick this angle and this angle. No, it actually needs to be the angle in between these two sides. It has to set up that way. It's not SSA, so we have to do SAS very specifically. Now let's look at some examples. Complete each congruent statement and state whether the SSS or the SAS congruence theorem is used to justify. If there's not enough information to make a statement, write NA. For example 1, we can see one pair of congruent sides, two pairs of congruent sides, but it doesn't look like we have any angles given. Besides, if we want SAS, it would have to be these two angles. So clearly SAS, that does not work because we're not indicating these two angles are the same. So now we can only try SSS. And here's where the third pair of sides are. And that's also what's special about this example. This side right here, it is in this top triangle. It is also in the bottom triangle. It is being shared. So that is going to be side, side, side. When two shapes share one side, that side is going to be, it's going to be considered as one pair of congruent sides on both shapes. Now the statement is actually where things get a little bit tricky. It's not just you see, oh, they both have this J and H. We can just put J in the front, H on the back, and write J, K, H. It's actually not. Remember, we have to write the shapes with corresponding points. So it's actually going to be H, K, J. The reason, I think that's this way. See, for the first one, JI, that starts from this point, which is we're using the shared side, going to the one that has the double bar. And that means for the other shape, we're going to do the same thing. The single bar line is going to start from the shared side to the double bar. So it's actually corresponding with H to K. And then J is just corresponding with H on the end. That is example 1. Example 2. I did make a typo in your notes. It shouldn't be JIH. It should actually be RST. And as you can see, one pair of sides, and then the angle immediately after the side, and then another pair of sides, and you can clearly see this angle is being included or in between the two sides. So this is going to be side, angle, side. RS is the one marker line. That is going to be corresponding with the one marker line, which is FG. So FGE is the triangle that is congruent with RST. That's example 2. Now example 3 and 4. I'm going to ask you to spend some time, have a look at these, and then you can come back and check to see if you got them right. For 3 and 4, the answer are actually going to be NA for both, because these are kind of the tricky questions. For example 3, this little arrow on the top means these two lines are parallel. Something you have learned before. This setup is called a transversal, when one line cuts parallel lines. And transversal is going to form, like say, these two angles. That's called alternate interior angles. So these two angles are alternate interior angles. and they are the same. When we just indicate two sides that are parallel, we're not indicating they are actually congruent. So we don't have any sides that are congruent yet. The only thing we have is one pair of angles, and we also have the shared side that we already talked about in example 1. This is a side that's being shared for both shapes. So we have one pair of congruent sides. But besides the angle and the side, we actually have nothing else. We don't know anything about these angles. We don't know anything about this side. We also even don't know these two sides. We just know they are parallel. We don't know they're perpendicular. They're congruent. Which is why for this, we only have one pair of angles, one pair of sides. That's not enough information. So we are going to write NA. In fact, here's an example of a shape that have one side of parallel lines and one pair of congruent angles. If I just make a trapezoid, I still have these two angles being the same, and I still have this side being shared. You can clearly see these two triangles are not congruent. We have to know if sides are congruent to make it congruent. Example 4. The answer is also NA. Some of you are like, well, I see one per bar, I see the double bar, so I already have side and side. Now I just need an angle or another pair of sides. We clearly don't know these two, so we can't conclude that. But if we want to use side, angle, side, it has to be this angle T and angle R. Clearly, that is not indicated at all. So we can't use side, 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 or side, angle, side. Now, some of you might remember you have learned about these two angles. They're facing each other. They are called vertical angles. So that's the hidden information that they are actually congruent. However, that angle is not included. It is not the included angle, so that is not used. That cannot be used for side, angle, side. That's example 4. Now lastly, example 5, 6, and 7. State what additional information is needed to make a congruence statement based on the given theorem. Example 5. These two sides are corresponding. These two sides are corresponding. So we already have one pair, another pair of sides. We just need a third pair of sides that are corresponding as the additional information. Well, we only have one side left in each figure. So the information would be GE is congruent with WY. Or you can flip letters to be EG is congruent with YW. That works as well. Side, angle, side, for example 6. These two sides are congruent, so we have the side. These two sides are congruent, so we have another side. Now we just need the angle. The angle in this case would need to be the one in the middle being included by the two sides. So it's going to be angle F. It's congruent with angle X. Something I want to mention is you can also name this as angle EFG is congruent with angle YXW. Typically, when you just have one angle with a letter, well, you can just use that letter, one letter to represent the angle. However, there are times, for example, if I say I have the E here, I have the G here, but F here, but I have more things. Let's say I have another line. Then in this case, you may see for angle F, I have this one, 1, 2, I have like 3 angles. So you just call that angle F is not clear at all. That's when we are going to use the 3-letter convention to name the angle. The letter that has the point for the angle is going to be in the middle, and then the other one, or the other 2 points are going to be next, one in the front and one on the back. Next, example 7. First, you only see the double bar, indicating these two sides are the same, so we at least have one pair of sides. And if you remember, we just talked about in example 4, these two angles are called vertical angles. So they are the same. That's basically our angle. But now if we want to find a side that are actually congruent, we got to remember this angle needs to be the included angle. So that kind of forced us. We need the side to actually form an inclusion with this side already. So it has to be these two sides. So ST is congruent to SD. You can name it as TS is congruent to DS. That works as well. That is example 7, and that is everything for this lesson. Thank you.